Hi, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 16. In this lecture, we'll discuss force, weight, and tension. These topics are covered in Chapter 5 of our textbook by Surway and Jouet. Roughly speaking, a force is a push or a pull of one object on another object. There are many different types of forces, and we will discuss many of them individually in turn, but for now we want a slightly more precise and general definition. A force, generally speaking, is the cause or agent of acceleration resulting from the interaction of two objects. So whenever two objects interact, like one person pushing on another person or planet Earth pulling on an apple, that interaction results in one or both of the objects accelerating, and the cause or the agent or the thing that brings about that acceleration is referred to as a force. As you think about forces, remember that there is a causal link between force and acceleration. So whenever you see a force in a problem, you should be asking yourself, what is the acceleration that results from that force? And of course, you should already know that acceleration and velocity are related. Whenever there is acceleration, there is a change in velocity. So at the end of the day, you should be asking yourself, if there is a force in a problem, what kind of a change in the velocity of the object will I observe? Also note that a force always involves two objects. One object exerts the force, another object experiences the force. One object is pulling, the other object is being pulled. So to be really precise, whenever we talk about a force, we need to specify the two objects that are involved. So going forward, we'll often talk about forces as being a force of object A on object B. We won't always put the subscripts there because it's a little bit tedious to write all that out. But whenever you think of a force, like the force of gravity pulling an apple down, you should really be thinking that's the force of one object, planet Earth, on another object, the apple. Note that force is a vector. That's why we put the small arrow on top of it. And therefore, like all vectors, it has a magnitude and a direction. The magnitude tells you how strong the force is. So if a force is very strong, we represent it using a long arrow. If a force is weak, we represent it as a short arrow. And of course, a vector has a direction that indicates the direction of the force. If you're pushing a table across the floor, you could be pushing it to the left or to the right, forward or backwards. The direction of the vector indicates the direction of the force. Force is something that we want to be able to measure and quantify. In order to measure it, we need a unit. The SI unit of force is the Newton, named in honor of Isaac Newton. It's denoted using the capital letter N, and 1 Newton of force is actually equal to 1 kilogram meter per second squared. At this point, it is not at all obvious why 1 Newton of force is actually equal to 1 kilogram meter per second squared. A little bit later, when we discuss Newton's laws of motion, this will make much more sense to you. Generally speaking, a force is anything that brings about or causes acceleration. But there are many specific types of forces that we will be discussing in this course in detail. Here I've listed some of the forces that we'll be discussing throughout the semester. Weight, drag, also known as air resistance, spring force, tension, normal, and friction are all specific types of forces that can cause acceleration. We'll be discussing each one of these in detail, but for now what I want to emphasize is that some forces have an explicit form or equation. So they're relatively easy to calculate once you know the equation and once you know the values of the parameters. You can plug those in and calculate the force. But we will also encounter forces that are reactive forces. Reactive forces are difficult to deal with, as you will see, because they require deduction. Reactive forces react to other forces involved in the problem. So as you will soon see, when you want to discuss tension or the normal force or the force of friction, you will first have to figure out what other forces are doing, and then figure out how these forces react to those forces. You'll see many examples of this soon, but as you learn about different types of forces, remember that some of them have explicit forms and some of them are reactive. The first force that we want to discuss in detail is one that you have known your whole life, gravitational force. Although here we want to talk about a very specific type of gravity. Here we want to discuss weight. Weight is the gravitational force of Earth on an object near the surface of the Earth. So weight does not refer to the gravitational force that the sun exerts on the Earth or the Earth exerts on the moon. Weight is a very specific and simple type of gravity. It refers to the gravitational force of Earth on objects that are near the surface. And when I say near the surface, I mean that their distance from the surface is small compared to the radius of the planet. A study of the gravitational force of the Earth on its satellites, for example, will have to wait until later. We want to have a precise expression for weight, and we will denote the force of weight using the letter W. We will put an arrow on top of it to remind ourselves that it's a vector. And to calculate the force of weight, we need to know the mass of the object and the gravitational field of Earth. The gravitational field of the Earth, denoted here using the letter G with an arrow on it, is really a series of vectors that basically surround the Earth. The gravitational field tells us which way the force of gravity acts. As it turns out, on planet Earth, no matter where you are on planet Earth, the force of gravity is going to be pulling you inwards directly towards the center of the Earth. So we can say that the gravitational field is a radial vector field. So it's a series of vectors. That's what makes it a field. And it's radial in the sense that all of the field vectors point along the radius. And in this case, they're pointing inwards towards the center of the Earth. The magnitude of these vectors is 9.8 everywhere, so this field is actually related to the gravitational acceleration that we have discussed before. If you know the magnitude and the direction of the gravitational field, you can multiply that by the mass of an object, and that gives you the weight of an object. The next force that we want to discuss in detail is tension. We'll often be interested in attaching a rope to an object and then moving that object by pulling on the rope. It's important to understand what the force is that the rope is exerting on the object if we want to understand the acceleration and the subsequent motion of the object. For that, we will need tension. Tension is the magnitude of the force that a rope exerts on an object attached to one of its ends. Here I'm using the word rope, however, you can replace the word rope with string or cable or wire. In this context, all of those things are used synonymously. Whenever we try to move an object by attaching a rope or cable or string to it and then exerting a force, we're essentially talking about tension. Tension is a reactive force, so I will not be giving you an equation for calculating tension. Tension reacts to other forces that are being applied. If you want to understand how this box is moving, you will need to know the tension in the rope. If you want to know the tension in the rope, you will need to know the force that the person is exerting on the other end of the rope. We'll talk about specific examples soon. It's important to emphasize some properties of ropes in physics land. When we talk about ropes, we are assuming that the length of the rope is fixed. So ropes, at least in the context of physics, in this specific conversation, do not stretch. If you want to talk about something that is stretchy, then you're talking about a rubber band or a spring, and we'll discuss the physics of springs a little bit later. So ropes have a fixed length, and also ropes have a negligible mass. Now, obviously, any piece of rope will have some mass. However, the mass of the rope compared to the mass of the objects that are attached to it is usually quite small. And so going forward, we will always ignore the mass of the rope. In other words, we will always assume, at least in this class, that the rope is light enough that we can ignore its mass compared to other masses that might be involved in the problem. An important application of the idea of tension is knowing when a rope can support a load. In other words, tension is responsible for the breaking of a rope. So if you're wondering, can I hang a 100-kilogram object from this rope, you must first be able to calculate the tension in the rope, and then any kind of a rope or string or cable that you're using for, let's say, industrial or engineering applications will have some kind of a specification associated with it, some kind of a load that it could bear. By comparing its load bearing to the tension, you can determine whether the rope is suitable for the task or whether it will break under the load. Here's a practice problem that involves both weight and tension. A bag of cement with a weight of 300 newtons is to be supported by ropes as shown. Two ropes are attached to hooks in the ceiling, forming angles 50 and 40 degrees. Each of the hooks in the ceiling can support a vertical force of 170 newtons. Can the hooks support the cement bag? On the face of it, the question is a relatively simple one. We're suspending a load from hooks in the ceiling, and we want to know if the configuration is stable. In other words, we want to know whether the hooks are capable of supporting this heavy load. The type of hook being used and also the method of installation is often accompanied by specifications. The specifications in this case state that each hook can support a vertical force of 170 newtons. So hooks normally can bear large amounts of force in the horizontal direction. Pulling a hook to the left or to the right is not a problem. The concern is pulling the hook in the vertical direction. In this case, if I'm applying a force of 160 newtons to this hook on the left straight down, we will not have a problem. The hook can support that force. But if I apply a force of 171 newtons, then the hook will get pulled out and will have a failure. Notice that the weight of the cement bag is given to us. The weight of the cement bag is 300 newtons. This is the gravitational force that the earth exerts on the cement bag. Ultimately, it's this 300 newtons of force that would be responsible for pulling the hooks out if we are going to have a failure. Given the weight of the cement bag, we could calculate its mass. Remember that the weight of the cement bag is given as mg. And also remember that g has a magnitude of 9.8. So given the weight and g, we could calculate the mass of the cement bag, although that will not be necessary. In this case, what's important for us is the weight of the cement bag. Notice that if you were dividing the weight of the cement bag equally between the two hooks, we would not have a failure in this case. The cement bag has a weight of 300 newtons. If you supposed that each hook supports 150 newtons of force, then this would be a stable configuration. However, also notice that these angles, theta 1 and theta 2, are not equal to each other. And because the situation is not symmetric, one of these hooks will bear more weight than the other one, and therefore there is a possibility of failure. If we want to answer this question precisely, we'll have to do a series of calculations. To answer this question, we'll have to systematically calculate all the forces that are acting on this complicated system. To begin with, we'll reduce the system to its essential points. So we'll represent the cement bag using 1 point. We'll represent each of the hooks using a point. And this critical junction where the three ropes meet, we're going to represent that using a point as well. In this way, we're going to avoid being distracted by superfluous features of the picture, and essentially, we're going to focus our attention on these 4 points only. We'll have to calculate the forces that are acting at each point. We'll start near the bottom of the picture because that's where we have the most amount of information. We're told that gravity is pulling on the cement bag with a force of 300 newtons. That's the weight of the cement bag. We're going to represent that fact using this blue arrow here. So the blue arrow points downwards, indicating that weight is pulling the cement bag down. We're drawing the blue arrow on this particular dot, indicating that this is a force that's acting on this object, on the cement bag. The magnitude of this force will be 300 newtons because we're told in the problem that the weight of the cement bag is 300. We need to be a little more precise. We will need the Cartesian coordinates or components of this vector. This vector can be represented as 0, minus 300. So weight or gravity is not pulling the object to the left or to the right. So the x component is 0. Weight is pulling the object downwards with a magnitude of 300. So the y component will be minus 300 newtons. If we want to have stability, if we want to have equilibrium, then something must support this force, something must balance the force of weight, and that's going to be tension. The cement bag is attached to this rope here. This rope is going to be pulling upwards on the cement bag. At this point, I don't know if this entire configuration is stable. I don't really know if the cement bag is going to stay where it is. But if we are going to have stability, then the force of tension needs to balance weight. So for now, we'll operate under the premise that this thing is stable. And then at the end, we'll check the validity of that assumption. If I want the cement bag to stay where it is, then tension needs to be pulling up with a force of 0, 300. Notice I'm not really using an equation here. I'm simply remembering that tension is a reactive force. In this case, tension is reacting to weight. If weight is pulling down with a force of 300 newtons, then tension needs to pull up with a force of 300 newtons. If you add these two vectors together, you'll get 0, 0. A force of 0 means no acceleration, because remember, force is the cause of acceleration, and no acceleration means the velocity does not change. And if the velocity does not change, that implies that the cement bag will remain where it is at rest. These are the only two forces that are acting on the cement bag. So now I'm going to move upwards to this point here, the junction between the three ropes. Since there are three ropes connected to each other at that point, I'm going to have three tensions. We can label these as tension 1, tension 2, tension 3. Tension 3 is the easiest one to figure out. Its components must be 0, minus 300. If I want this piece of rope here to remain where it is, then I need the net force on it to be 0. In other words, I want the force at the top to balance the force at the bottom, right? So at the bottom, we have a tension of 300 newtons. At the top, we must have a tension of 300 newtons. If you're pulling on the two ends of a rope and one end is experiencing a larger force, then the rope is going to move in that direction. Here I've chosen this force to be 0, minus 300, because now if I add this vector to this vector, once again I'll get a net force of 0, and 0 force means no acceleration. No acceleration means no motion in this context. Calculating T1 and T2 is going to be a little bit trickier because those two point at an angle. But I can now imagine a horizontal line like so. I can see that this horizontal line is parallel to the line of the ceiling. And I can also see that this rope on the left, rope 1, is a transversal. It's intersecting those two parallel lines. So if we have theta 1 at the top, then this angle here must also be theta 1. Similarly, this angle here must be theta 2. Now that I have the angles, I can calculate the components of each one of the forces. As usual, I'm going to draw a right triangle. Then I'm going to use sines and cosines, so trigonometry, to calculate the x and y components of this force. And then similarly, I'm going to calculate the x and y components of this force. I'll let you carry out the details there. The end result is that on the left, I'm going to have a force whose x component is minus t1 cosine theta 1, and y component is t1 sine theta 1. Notice the x component is negative because this force is pointing to the left. Similarly, on the right, I have a force whose x component is t2 cosine theta 2 and y component is t2 sine theta 2. At this point in my analysis, I do not know what t1 and t2 are. I'm hoping that I can calculate those eventually. I do know what theta 1 and theta 2 are. Those are given to me in the problem. So these are the three forces that are acting at this point. I can now move upwards to the hooks themselves, which are the main topic of interest here. Each hook is attached to a rope, and so there must be a force of tension acting on these hooks. The force of tension always acts along the length of the rope, and if I want this rope on the left to be in equilibrium, then the force at this end and the force at this end must balance each other out. That tells me that near the top, the force must be t1 cosine theta 1 and minus t1 sine theta 1. I still don't know what t1 and t2 are, but if I know that the force on the left or on the right side of this rope is this vector here, then to cancel that or to balance it, I know that the force on the left side must be this quantity here. Similarly, for the right rope, for rope 2, I've chosen the force at the bottom of that rope and the top of that rope to basically balance each other out so they can cancel each other out. A net force of 0 means 0 acceleration. 0 acceleration means no change in velocity. So at this point, I have written down at least expressions for all the forces that are acting on the critical points or junctions of this problem. I now need to actually calculate numerical values. I need to specifically calculate T1 and T2. Once I have numerical values, then I will calculate the y component here and the y component here. These two numbers will be critical for us. Remember that each hook can support a vertical force, a force in the y direction of 170 newtons. So I will need to know if these two numbers are greater than 170 newtons or not. To calculate numerical values for tension 1 and tension 2, I'll focus my attention on the junction. If I can figure out all the forces that are acting on the junction, then I can figure out the forces that must be acting on the hooks. And if I can figure out the forces that are acting on the hooks, I can answer the question of whether they'll be pulled out or not. Focusing on the junction, if I want equilibrium, if I want the net force to be 0, if I want that junction to remain where it is, then I need these three forces acting at the junction to add up to 0. More precisely, I need the x components to add up to 0, and I need the y components to add up 0. That gives me two equations. The first equation basically says that the sum of all of the forces in the x direction must be 0. That's our expression for equilibrium or stability. And when I look at the x forces, I see that I have minus t1 cosine theta 1 there, and I have t2 cosine theta 2 there, and I have 0. I'm going to add these three forces together, and I expect them to add to 0 if we're going to have stability. This gives us one equation and two unknowns. Remember that we know what theta 1 and theta 2 are, but at this point we don't yet know what T1 and T2 are. We don't know what the tensions in the top two ropes are. So we'll need another equation. By looking at the y forces, we can get our second equation. So if I want to have stability or equilibrium at this junction, I need this quantity here plus this quantity here plus this quantity here to add up to 0. In other words, I want the sum of all the forces in the y direction to be 0. So the sigma here is denoting summation. Hopefully this is notation that you're familiar with from your math class. The point here is basically that I want all the upward forces to balance all the downwards forces. In fact, this equation 2, you can bring the 300 to the right side of the equation, and then you can clearly see that the y components of the tension forces pulling upwards must balance the y component of weight pulling it downwards. That's essentially what this equation is telling us. Now notice I have two equations, equation 1 and equation 2, and we have two unknowns, t1 and t2. So what we have is a system of equations, a system of two equations with two unknowns. Hopefully you know how to solve systems of equations. You basically take one equation and solve for one of the unknowns, for example t2, and then you plug that into the second equation and then you solve for t1. So I'll let you carry out the messy algebra of this. This is something that you should practice with, but the end result is going to be this. We'll find that T1 is equal to weight. So this weight is basically this 300 newtons that we were talking about earlier. So lowercase w is basically equal to 300. And if we divide weight by sine theta 1 plus cosine theta 1 times tangent theta 2, then we will get the numerical value for T1. You might be wondering, where did tangent of theta 2 come from? Well, when you solve for T2 in the top equation and you plug it into the bottom equation, you will end up with sine over cosine. And remember that sine of theta over cosine of theta is just tangent of theta. I know what all the angles are, 50 degrees and 40 degrees, so I can plug those numbers in, and I find that the tension in rope 1 is 229.8 newtons approximately. I can also plug numbers into our expression for T2. Remember that if you solve this equation 1 for T2, you'll see that T2 is simply T1 cosine theta 1 divided by cosine theta 2. Now that we know what T1 is, we can plug that in here, and we'll find that tension 2 is 192.8 newtons approximately. Now, we can't answer the question just yet. All we have found is the tension in the rope, but remember that this force of tension is acting both in the x and the y direction. So I'll want to calculate the x and y components separately. Looking at our pictures over here, we have expressions for the x and the y component. So I can now take the magnitudes and calculate the x and y components. If I do that, I'll find that the tension in rope 1, remember this is a vector quantity, has an x component of 147 approximately and a y component of minus 176. Tension 2 in the second rope will have an x component of minus 147 and a y component of minus 124. So I obtained these numbers by plugging in tension 2 into these two expressions near the top. I am now finally ready to answer this question. Remember that each hook can support 170 newtons of vertical force in the y direction. As I look at tension 1, I can clearly see that its y force is minus 176 newtons, which exceeds the specification for the hook, so the left hook will get pulled out. This is what engineers sometimes refer to as a cascading failure. At first, it seems like hook number 2 is perfectly safe and only hook 1 will fail. But of course, once hook 1 gets pulled out of the ceiling, the cement bag will swing to the right. All of its weight will be placed on the second hook. And so eventually, the second hook will also fail and the entire cement bag will fall on the ground, a total disaster. This is a rather complicated problem that combines multiple tension forces with weight. It requires a lot of careful analysis. It bears some thought, so spend some time going through this calculation in detail until you fully understand it. And that's the end of this lecture. Thank you for your attention.